Okay, yeah, so I just open the file first. Okay, so we're going to continue, and from last week, right, we've seen that we can actually, do some inference, right? For example, find the predictive distribution and so on. Find the credible intervals for the posterior distribution. Okay, so now we going to see that you can update or you can use the Bayesian method sequentially, right? Meaning that you can actually update the posterior. This is where the exchangeability actually matters, because if you have it to be independent, right, it means that the past does not affect the future, but because we assume that the data are exchangeable, right? So this is where you can see that we want to use different data, and we want to keep the current data, the effect of the current data in the model, and then we want to update based on the new data coming in. Okay, so suppose that we have two data, which is X and Y, right? And then so we have our posterior distribution, which is theta given X and Y. So this is actually X, the likelihood or the joint PDF of X and Y given theta, condition of theta, and the prior of theta, p theta, right? So you can see that actually the joint of X and Y given theta times the prior, right? You can actually rewrite it in the form of Y given X and then theta given X. Okay, so this one, okay, so this from here to here is just this is a conditional, go to the joint PDF of X, Y, theta, and then we go to another, a different kind of conditional, which means Y given X theta times X theta, right? And then X theta is a joint, so you can go, this one can go to a conditional of theta given X times Px, right? And then Px is because we assume the data is a constant, that's why it's conditional, it's proportional to this Y given X and theta given X. Okay, so this means that if I were to have a data, right, Y, I can actually update it based on theta given X. Okay, so this means that if I have two sets of data, for example, X and Y, or you can say a joint of X and Y, then it's actually proportional to the likelihood or the joint PDF of Y, sorry, the conditional of Y given X theta times the theta given X. Okay, so this means that we can actually update first by X and then we update by Y. Right, so here, this means your X comes first. So your X comes first and then you have your Y. Okay, so this means that you need that number one is this one, the first one is a posterior, right, of theta given X. Okay, and then you have your new joint PDF or your likelihood, right, of your Y given the previous data X and the parameter theta. Okay, so if you were to look at the old or the normal, the usual posterior, right, it will be theta given X is actually proportional to X given theta times P theta, right? So this is the usual posterior. Okay, so if you compare this to our new posterior, you can see that you have your Y and then you have your X theta and then you have theta given X. So the first one actually assume the role of the prior, of course, given X, and the Y given X theta assume the likelihood given X. Okay, so they are not similar, but they play the same role. Okay, this means that if I were to have a data, and then I can get the posterior given the data, X for example, and then I have a new data, Y. So it doesn't mean that I get rid of the information about X, right? I can just incorporate my new Y into the posterior of theta given X, and then I get a new posterior, which is theta given X and Y. Okay, right. So if we look at our previous example, which is the cancer treatment binomial example, right? And say that we have the a new data, right? So we have an additional patient, right? And we know already that from these 70 patients, so we have a new patient. For example, this would be your M or whatever, and then you have 34 survive. So this is your Y. Okay, so we want to update our existing information. Okay, so if we look back at, do I have, okay, all right, I have this chapter 2, maybe. Yeah, okay. So if you look at our example, right? Oh, sorry, this one is without. Okay. Oh no, I didn't. Maybe I didn't save it. Okay. All right. Yeah. Okay. Sorry, I didn't. I think I didn't save it. Okay. Right. Okay. So anyway, if you look back at the example from week 1, which is but it's in chapter 2. Let me see. Oh yeah. Okay. So in the end, at the end actually we have our posterior, right? So our posterior was actually the theta given Y was actually beta, right? And then we have 17, 24. Okay, so this was from the example. The posterior of theta given Y was actually beta, right? So now we have new data coming in. Okay, so if we look at the posterior, all right. Okay, and so it was actually, I think theta, let me see, it was 17, 16, right? 23. Okay, so this was from the previous data. Okay, so now we have a new data, right? And say that we have, well, this is Y. Maybe we should use something else, say Z. So we have our new data, and the data is maybe Z, right? Should we use Z? Okay. Right. The notation wise, I mean, you can actually either use new Z, or okay. So if you were to treat it as a prior, okay, so you can actually also happen here. You can actually just also write it as, instead of P theta, right? You can also put as a prior, right? So this is actually your previous posterior is now your new prior. So you have, is actually your beta 1724. Okay, so you have your new data, right? So your data here is actually, right, binomial, and then you have 70 and 70, and then you have your parameter theta. Okay, and in this data, actually, your Y is actually 34. Okay, right? So, and then meaning that if you look at the previous example, right, you can write your likelihood actually. So this your likelihood or your joint PDF, right, is actually proportional to theta, and then you have your y, which is 34. Wait, is it 34? Yeah, y, which is 34, and then you have 1 minus theta, which is, and then n minus, which is 70 minus 34. Okay, this is binomial, right? If you look at the proportion of binomial, so this is 34 and then 1 minus theta, n minus 34. Okay, which is 36. Okay, so then your new, the new posterior, right, would be theta given y, which is your theta or your likelihood, your joint PDF times your prior. Okay, so now your prior is actually the new prior, right, which is from your old posterior. Okay, and this, if you multiply these two things, okay, so you will get theta, which is 50, right? 50, and then 1 minus theta, which is, I think is 59. Okay, and then if you were to compare it to beta, okay, so this is actually beta 51, 60. Okay, so this is actually the kernel of a beta. Okay, kernel of the beta, right? Okay. Okay, so this means, right, if you, okay, so either you want to use, so actually either you can actually use this sort of notation, right, meaning that you want to put x and y and so on. So you can actually do this, right? So if, for example, just now, if you put a z, if you put the prior here, for example, you put the prior is y, and then you have your new data is z, so then you will have actually y and z. So this will be z theta and z theta and y, and then you have theta given y. Okay, or if you were to treat it as a new prior, right, you can also put it just as p theta, right? So both are okay actually. Okay, and then if you do it like a new prior, then you just use y theta as the likelihood, or or the joint PDF, right? And then you can see that it's the same. Okay, so now you have new prior, and then you have the new data, and then you have the new posterior, right? So that meaning that after you update the data, right, where you have your n is 70, and then your y, the number of survive is 34, then you actually have a new posterior beta and parameter 51 and 60. Okay, and if you look at the new posterior mean, the mean, right, the mean of this beta, so beta is actually should be alpha plus beta, so the mean is actually 0.46. Okay, and then you have the 95% credible interval is around 0.37 and 0.55. Okay, so if you compare it to your old mean and the old mean and the old credible interval, okay, so actually, right, so before we update your data, the old mean was actually, from your previous example, right, it's actually 0.4 2, right? And the all credible interval is actually, I think, 0.29, wait, 95. Is it 95 or 90? Oh, okay. Right. So I think I didn't give you the 95% credible interval. Okay. Yeah, I didn't. Sorry. Okay. So this one, if you want to find it, we have to find it anyway. But the old mean is actually 0.42. Okay. And the probability, oh yeah, this one we have the probability of theta bigger than 0.4. If when it's better, right? Then given theta, the old one is actually 0.57. Okay, so we can actually find this with the new distribution. Okay, and oh, right. Okay, I have to find it. I think I write it out, but it's missing somewhere. So anyway, I'll try to find we can calculate it later, but I think I'll try to find it after this. So anyway, so one thing you can see, right? Then after we update, then the mean will obviously change, and actually the credible interval and the probability will also change a bit depending on the new data actually, because the old posterior was 1724 and the new posterior is 5160. So then there are changes to the distribution. Okay, as you update the posterior. Okay, right. So this is when this is one of the example, right, where you can see that we can actually update your posterior as we get the new data, but we still keep the information about your current data, and then we just include the new data into the posterior and update the posterior. So this is one of the advantage, right, for the Bayesian, right? So we don't have to discard or recalculate whatever, we just update, because it seems it will be the similar distribution, right? It's just that the parameters will be updated according to the new data. Okay, so this is updating the posterior, right? So now we're going to go into like a bit more, well, can't really say technical, but a bit more theoretical, right? Because we have to look at transformation. Okay, and this is where, because sometimes we are more interested in a function of a parameter rather than the parameter itself, right? For example, if you have a binomial, we might be interested in the odds of success, for example, theta 1 minus theta, rather than theta itself, right? So this means that when we do this, we need to transform the prior and or the posterior from one parameterization to another, meaning that we have to transform the parameter, and that means we have to transform the distribution, the prior, the likelihood, and also the posterior. Okay, so there are actually two ways, you can see later, right? So the one way is you have to transform the prior and the likelihood separately, right? Or you can actually find the posterior and then transform to posterior directly. So actually both are okay, depending on which one is actually easier, because when you change the distribution or you find the posterior, sometimes the transformation will be harder. So sometimes transforming it separately, the prior and the likelihood, is actually easier than transforming the posterior sometimes. Okay, but both should give you the same answer, right? So if you transform before or after you join the prior and the likelihood, they should give you the same distribution either way. Okay, so suppose that we have a data, we have the parameter theta, right? Okay, and we have the likelihood, which is L theta, and we are interested in phi, right? So phi is a function of theta. Okay, so G here is a function. Okay, right. And so if we specify a prior in terms of theta, right, we get a posterior in terms of theta given y. So what will happen to the prior and the posterior about phi? So if you have a function of theta, phi, right? So what will happen to the prior and posterior if we transform from theta to g theta, which is your phi? Okay, so first, right? So we're going to look at the prior. Okay, so we have your prior distribution p theta, right? And then we have the prior belief in terms of phi, which is a phi, p phi, right? Okay, so here this is where you have to use your transformation technique, right? So usually it's actually apart from using the CDF, it's actually easier to use the change of variable technique. So actually up to you, right? But here I'm going to use a change of variable technique. And if you have a discrete and continuous, the difference here is the continuous has the Jacobian, right? Where you have to transform, sorry, you have to differentiate the theta given theta over phi. Okay, so the difference here is the Jacobian because the discrete does not have the Jacobian, right? So yeah, there is a partial. So here is a partial derivative in case your theta is more than one parameter. Okay, but don't worry, for our course, we are just looking at one parameter for this transformation, not more than one. Okay. Okay, so here, okay, so if you have your prior, means that you have to use the transformation, for example, change of variable technique, then you have to transform from theta to phi. So it means that you have to change or you have to transform the PDF of your p theta to p phi. Okay. Okay, one thing, okay, so now if you look at this one is for the prior and for the likelihood, right? The likelihood is invariant to transformation of the parameters. Okay, what does the invariant means, right? Invariant means that you can see over here, it does not have the Jacobian. Okay, so this means that if I were to have y given phi, right, it's just that anything with theta, I just change to your g inverse phi, right? So then I just put my g inverse phi inside the original, I mean the original likelihood. I just change from theta to g inverse phi, right? And then simplify or edit, and then that's my likelihood. Okay, so compared to the just now, right? Compared to the prior, right? This has a Jacobian, but for the likelihood they don't have. Okay, this is what is called invariant to transformation. So it doesn't matter if it's discrete or continuous. In both cases, they don't have Jacobian. Okay, so you can see over here, if I were to find the likelihood of phi given y, right, which is proportional to my joint PDF, then again, it's just, I just use my likelihood of, so this is actually the joint PDF of theta. So this means the likelihood of theta, right, theta is likelihood of theta. That means that means that my theta inside my likelihood, I just change to my G inverse phi. Okay, G inverse phi is you have to find a function of phi. Okay, so because in the transformation is phi equal to G theta. All right, phi equals to G theta. This is your original transformation. So you have to change or you have to move your function here, and then you have to get a function of theta in terms of phi. This is your G inverse phi. Okay, G inverse phi, and then after you change, you get this is in terms of phi, it's a function in phi. This thing is the one that you put back inside the likelihood of theta. So anything with theta, you just change with G inverse phi, and then you get your likelihood. That's it. Okay, so that's why it's called invariant, because it doesn't have Jacobian or whatever. So as long as you can find this G inverse phi, then you can just put it inside the likelihood and you get your likelihood of phi. Okay, right. So this means that the maximum of your likelihood of theta occurs at the same point as the maximum of the L phi. Okay, so the MLE or maximum likelihood estimator for phi is just a function of your, so this means that the MLE for phi is just a function, of MLE of theta. Okay, so that's why you have here phi hat is actually G theta hat, meaning you have theta hat is the MLE of theta, then you get a G, right? Because your phi is actually your G theta, right? So now you just put in your theta hat inside the function G, and then you get MLE for phi. Okay, right. This is also another reason why the likelihood is invariant to transformation, means that the MLE, you just find a function of the MLE, then you get the MLE for the new function. Right? So then, if we were to combine the prior and the likelihood, we have the posterior. Okay, we have the posterior. Then the posterior for phi is just the likelihood for phi multiplied by the prior for phi, right? So you have the likelihood. This is function for the phi, right? So this is from the likelihood, from the transformation of the likelihood of theta, and this is transformation of the prior of theta. Okay, and this is also, and this is actually, you can see over here, this is just a transformation, meaning that you find the G inverse phi here, and you put into the posterior of your theta, and then multiply by the Jacobian. This is where I say, right, so you actually, there are two ways for you to do the transformation. So you either transform the likelihood separately, and then you've transformed the prior, or you can actually transform the posterior after you obtain the posterior of theta given y, then you do transformation on the posterior itself. Okay, so both are actually correct. I mean, should give you the same answer, right? The difference here is no difference. The difference in the method is, as I said before, because likelihood is easier to transform because it's invariant, right? You just put in the function, and usually the prior is simple. So if you want, when you do the transformation for the prior, it's actually simple. So that's why then that's why sometimes you can do it separately, or you can actually find the posterior and then do the transformation on the posterior itself. Okay, right. Now we're going to look at example. You might be wondering, right, like how we are actually doing this. Okay, so now we're going to look at the example. So we have your data is y given theta with prior beta, right? And you using the odds for transformation, phi is theta given 1 minus theta. Okay, so this one, this is actually similar to what we did for the previous example. I think it was example where you have I think there was example before that we have, right, I can't remember, but yeah, I think it's the earlier part of chapter 3, right? We have this example, but anyway, right? So if you were to find this one, let me see. Oh, wait, I think. Oh, all right. So okay. So now we have. All right. I think we need more space. Okay. So now if you have the prior, right? So prior is a beta, right? So beta AB. So if you are already good at it, right, you can just write the kernel out, right? So this is kernel of a beta, Okay, you can use proportional, right? So you don't have to put write the full PDF. You can write the kernel. So this is your prior. Okay, and then you have your likelihood which is a binomial. So from our example, we already know, right? Before, this is the kernel of a binomial. Okay, or the likelihood, because the kernel of the join of the PDF, sorry, PMF of a binomial. So this is also the likelihood. So this why it's proportional, right? And then you have the posterior, right? It should be beta. Okay, but now we are interested, to see the kernel. Okay, right. So here, okay, one thing, right? So because we are looking at the at the distribution, so the transformation we can also use sort of proportional when you're using transformation. Okay, so this means, right, for example, if you want to find the prior, because this is just a kernel of the prior, right? I mean, you can also write the full PDF. Okay, but if we want to use just the kernel, also okay, because it's only because when we do the transformation, it involves the theta, right? So it doesn't involve the constants, right? Okay, so then we have our transformation, right? So we have our phi is equals to a function of theta, which is your theta 1 minus theta. Okay. Okay, so this is now your skill in maths. You have to move it around, right? Okay, and then you should get theta, which is your G inverse phi, is actually phi 1 plus phi. Okay, right? And okay, just for illustration, how do we actually get the answer? So meaning you have to move your phi, right? So first, you just go 1 minus theta, go up, right? Then you have phi theta equals to theta. You have theta 1 plus phi equals to phi. Okay, so you just, meaning that this is algebra, you have to move around your phi and your theta. Okay, so the aim here is you have to get a function of your theta in terms of phi only. Okay, so your theta equals to something which is in phi only. So you have to move around this equation, right? You have to move it around such that, in the end, sorry, I think, is this? Oh, okay. So this is not, right. Oh, yeah. Okay, so this is actually theta. Oh, I need to write it properly. Okay. So then if you move this to this side, right, you have to move this to this side, and then you get theta, and then theta plus phi theta. So you take out your theta here, and then this equal to phi, and then you get theta is equal to phi over 1 plus phi. Okay, so this means your theta is a function of phi only, right? So this is why it's called a G inverse phi, because it's a function in phi. Okay, right. So after that, after you have found your G inverse phi, so then this is where you can find the transformation. So for example, if we look at your prior, right, of phi, right, this would be the Jacobian, or so first is the phi theta G inverse theta. Oh, okay, all right, sorry. I think I keep writing the wrong thing. Okay, phi theta, right? Okay, Jacobian. Okay, and then if you remember that, okay, and here the Jacobian, right, means that you have to differentiate your d theta over d phi. Okay, so d theta over d phi is actually you have to differentiate this function, this one, meaning you have to differentiate your phi 1 plus phi. You have to differentiate this, right? Okay, and this is where you will differentiate and you have to simplify, and you should get phi, let me see, power 2. Okay, so you have to do this. Okay, and then so you have to find the Jacobian first. So this would also why it's important to find this function theta, which is a G inverse phi, because this one is the one that you have to differentiate. So you have to differentiate this function, right? And the likelihood of theta is actually your original one, right? Which means this one, this kernel of a beta, okay. But here you just input your G inverse, okay. So meaning that anything with theta, right, you have to change with phi 1 plus phi. Okay, so the kernel of the beta just now would be, theta a minus 1, 1 minus theta b minus 1. So we have theta, so this one is phi a minus 1, and then we have 1 minus theta b minus 1. Okay, multiply by Jacobian, which is this one. It's too long to write. Okay, I might run out of page at this rate, too large. Okay, and then after again, this one had to push proportional because I only use the proportional part. Okay, and then after I simplify, I actually get phi. This one is after I simplify, okay, everything a plus b. Okay, right. Okay, so this is the prior. Okay, and then if I were to find the posterior, right? If I have my likelihood times my prior. Okay, so this is my prior actually. This one at the top. This one is my prior. Okay, so then the likelihood would be, because now we have, if you remember, the likelihood is actually the kernel of a binomial. So this is your likelihood. So what happened here is your theta, you just replace your theta with your G inverse phi. Okay, without the Jacobian. Okay, so you have your binomial, then your kernel, so it's just your theta y, 1 minus theta, n minus y. So you have phi, your theta y minus theta, which is your G inverse phi, right? N minus y, and then multiply by your prior, which is your just now, right? A plus b. Okay, so then you will have phi y plus a minus 1. Okay, so this is the kernel. Okay, so what happens here is actually, if I were to rewrite this, okay, so this is actually the kernel of a F distribution, which is very complicated actually, but Anyway, just for information, it's a F distribution, right? And here, if it's F distribution, then it's actually you have F distribution. For example, you have V1 and V2. Okay, so your V1 here is actually 2 times Y plus A, and your V2 here is actually 2 times N plus B minus Y. So this is actually, okay, so this is actually, wait, 2, oh yeah. Okay, because what happened here, this would be, this is 2 times this divided by 2, and this is actually 2 minus Y. Yeah. Okay. Yeah. Maybe something. Okay. This is. Why is it? You will think it's a bit complicated because. Okay. Let me save it. Okay. I'll just show you the PDF, right? Or no, the F distribution. Okay. Because. Let's see. Okay. Yeah. Okay. Here, right? You can see. Okay. Yeah. So this is it the F? Okay, right. So if you look over here, right, this is actually the okay, smaller. Okay, yeah, this is the F, right? You can see over here is F, right? Is FV1, V2. Okay, and here your your variable is X. Okay, so if you look over here, the kernel is actually this part. I just write in red, right? This is your kernel, right? So just now is a kernel of F, right? So you actually your F will actually be, here is X. So V1 over 2 minus 1. And then you will have over 1 plus V1 over V2. And then you have X, right? Power V1 plus V2 divided by 2. Okay, so you can see over here, right? Yeah, it's quite complicated. So the rest are actually constant. So you can see here that just now, that's why I said the V1, that's why I have 2 there, because V1 over 2, so it's 2 times something divided by 2, right? And then you have this, and then you have this is V1 plus V2. Okay, so this is actually the kernel of the F distribution, right? And we have V1 plus V2, and okay, I shouldn't save it. All right, it's okay. Okay, so if you look just now, okay, you see just now, right? So here, this is your V1. That's why I say V1 is actually 2 because you divide by 2, and then you have this would be okay. We assume V1 and V2 are equal because there V1 over V2 would be equal to 1, right? And then we have it should be that your V1 plus V2 will be should be equal to your A plus B plus N. Okay, so if you look over here, Y plus A plus N plus B minus Y, you should get A plus B plus N. Okay, so that's why this is actually a kernel of F distribution, V1, V2, with V1 and V2 as given here. Okay, so yeah, it's a complicated distribution. Okay, but in this case, it's just okay. So sometimes, okay, this is where later when you learn about the simulation or whatever, if you can identify the distribution, then that's good, right? Because it's a known distribution. But sometimes, right, we will arrive at the very complicated posterior, and it's not a known distribution, and that's why we have to use simulation later. Okay. Right. Then, okay, so this is example, right, of where we have your transformation. Okay, so we're going to look at this example later. Okay. So one thing, okay. So then what happens, right? What happened to all the what you call it? What happened to all the things that we can do with the distribution, right? After we do transformation. So one thing is the MLE or the maximum likelihood estimator have actually invariant under renormalization, meaning that this is what we already talked before. If I have theta head is MLE for theta, then the phi head is function of your G over the MLE of the theta, which is theta head. Okay, so this means that if I find the theta head, MLE for theta, I just use the function and then I just input my theta head into the function, I get MLE for phi. So this is again like invariance because you don't have the Jacobian or whatever. You just the function, you can just put the function inside and then you get the answer, right? But what happens is the MLE, right? So okay, why is the MLE invariant? Because remember, MLE is based on your likelihood, right? It's based on your likelihood y given theta. So as I said before, your likelihood is invariant under transformation. So that's why your MLE is also invariant under transformation. Okay, so one good thing about the MLE, right? But what about the posterior summaries? Because now we have a posterior distribution, right? So we want to use the posterior distribution to find the summaries, like the mean, median, variance, and so on. So what happened to that for Bayesian? Okay, so if you look at the mean, the posterior mean, which is the expectation of theta given y, right? However, in general, the posterior moments are not invariant, right? Because the expectation of phi, the expectation of a function of g theta is not always equal to the expectation of a function is not equal to the function of expectation. Okay, unless it's a linear transformation. Linear means like 2x, 3x. Because if it's a linear transformation, then it will be the same, because when you have linear transformation, you have constant, right? So if, for example, if I have x, or I have 2x, then the mean of 2x is actually 2 times the mean of x. That's actually a linear transformation. But for example, I have a function of theta is a theta square. So expectation, remember, right? Expectation of a theta square is not equal to the expectation of theta square. Okay, so this is wrong. Okay, so this is for example, right? This is one of the example where this is not correct. So expectation of theta squared is not equal to the expectation of theta squared, right? When it's a linear, right? Linear means expectation of 2 theta is equal to the 2 times expectation of theta. So if it's linear where you have a constant, then yes, you can actually take out your function, whatever, and then multiply because it's a constant. That's why it's a linear transformation. Okay, so this is correct. Okay, but if it's not a linear transformation, then it's not correct. So that's why, and this is true not just for the mean, it's for any moment, right? Like the moment mean like the first moment, the second moment. So this is the second moment, right? The first moment, second moment, third moment, whatever. So they are not invariant, meaning that you cannot find a function of the expectation to get the expectation of the function. Okay, so this is not true. This is not true. Okay. Okay, so this so they are not invariant, right? So you cannot just use the function of the mean or the function of the expectation to find the expectation of the function. Okay. So that is for the expectation part. But how about the median and the quartiles? Okay, so median, if you remember about the median, right? Median is where you have the probability of less than m is actually 50% or 0.5. Okay, so for example, if we have a distribution, right, this height. So if I find the median, okay, so this is my fx, right? This is my x. Then if I can find my median, so this is my m, then the probability under the curve is actually 0.5. Okay, so the median means that the probability of theta, or in this case s, right, probability of theta less than m, which is the area under the curve, is actually 0.5. So that's the median in terms of probability. Okay, so 0.5 here. Then, okay, so what if we looking at this terms, the median in terms of probability? Then we have theta less than m, right? Then we have a function of g theta is less the function of gm. Okay, and so g theta is a phi, right? So gm is actually the median of the posterior distribution expressed in terms of phi. Okay, so this means that if I have any quantile, right, any quantile as q, where the probability is q, so this means, right, is in general, right, if you have this quantile, so this is my s, right, and then s theta, and the probability of theta less, this probability here is actually my q here. So s is my quantile. Okay, quantile means is like percentile, like quantile 0.5, 0.3, 0.1. So it doesn't have to be 0.5, 0.1, 0.2, 0.5, and anything between 0 and 1. Okay, so if you use the same step as at the top, right, we can show that the quantile is just a function of the quantile of q, sorry, the quantile of theta. Okay, so meaning that it still preserves the probability. So if you change from theta to phi, right, if you change from theta to phi, and then you change it from SQ to s theta to g s theta, okay, they still have the same probability, which is q. Okay, so this means that the quantiles are invariant to transformation. Okay, okay, so what does it mean here, right? If I were to have the quantile, for example, right? So if I were to have the quantile for my theta, then I just apply the function. So if, for example, I have a quantile, for example, phi is g theta. Okay, then I want to find sorry, not g phi. Phi is g theta, right? So then I find the quantile, for example, some quantile, right? So then I just apply this function g to the quantile, and then I get a quantile for phi. Okay, so that means it's invariant, meaning that you don't have to, you don't have to find Jacobian whatever. So you can just apply the function g, and you can get your value of phi for quantile. Okay, and this means that the credible interval based on quantile are also invariant to transformation, right? Meaning that if I have a credible interval for theta, okay, I just apply, then to get a credible interval for phi, for example, I have a, right, is a and b. Then I just use this function g. So credible interval for phi is just, I have a function of g, I put this value of a in, then have a function of theta, right, g, then I put my value of b in, then I can get my credible interval. So I don't have to, through transformation, I don't have to find the distribution of phi even, right? I just have to know the function g, and I use my g theta, right? I just change from my theta, I put in my a and b, I put ga, gb, I can get credible interval for phi. Okay, so that is one of the advantage, right? For if you use a quantile of the posterior, means it's also applied to your credible interval, because credible interval is based on the quantile, right? For example, if you have 95% credible interval, you will use 2.5 the quantile of 2.5, and then so percentile of 2.5 is actually quantile of 0.025, and then you have a quantile of 0.975. Okay, so that's why the credible interval is based on quantiles, so it's also invariant to transformation. Okay, so there's one big advantage actually if you use transformation for the credible interval. Okay, the last one is maybe the mode. Okay, so the mode occurs at the maximum of the posterior, right? So the theta, for example, theta tilde maximizes the log posterior. Okay, and the mode theta tilde maximizes. Okay, so maksudnya, so if you look at the, wait, is this the typo? Okay, let me see. So theta log py. Okay, wait. Log posterior. Okay. Right. I have a feeling that, okay, this is actually a typo. I think this, okay, so this originally, right, this is your log posterior of the theta. Okay, so I have a feeling that this is actually log p phi actually. Phi given y, right? Because this is your y and this is your likelihood or your GPDF of your G inverse phi, and this is the likelihood of your phi times Jacobian. Okay, I mean the log, I guess. Okay, so this is actually log phi. This is must be a typo. So this is originally your theta tilde maximizes the log posterior of theta given y. Okay, and then you have your phi. Okay, then you have your log phi, right? Which is your log of your after transformation, and then plus the prior after transformation. Okay, and then your theta tilde equals to your G theta tilde, meaning that this equal to this. I mean, you can just transform from here to here only if this your Jacobian does not depend on phi. Okay, so as I said right before, right, because usually your prior is not invariant. Okay, so this means that the posterior modes are not invariant to transformation because of the Jacobian thing. Because without the Jacobian, this one you just put your G inverse here, and your log P theta, you just put your G inverse here. So actually, without the Jacobian, this one will go to this, right? This one will go to this. Then actually, it's actually invariant. But because we have the log Jacobian here, that's why it's not invariant. It's only invariant, it's only equal if the Jacobian does not depend on theta. If this Jacobian is a constant, right, and you log the constant, of course, then it does not matter. Okay, but in general, that's not true. Okay, because of the Jacobian, that's why it becomes not invariant to transformation. Okay, so the modes here are not invariant to transformation. Okay, so and if we are interested about phi rather than theta, we need to do analysis in terms of phi, not theta. Okay, so this whole thing has been on the. Okay, sorry, wait a minute. I need to actually open my something I like actually. Okay, right. Oh, right. Okay. So now we are going to look at example part to see, right? Okay, so this is previously, right? We have the example. Okay, we have the example. We have the theta say that the theta given the posterior is beta 22, right? And we are interested in your phi theta in the transformation, which is your phi theta y minus theta, which is the odds, right? And we want to compare the summaries for theta and y. Okay, so this is actually related to your previous example. Let me see. Where is it? Is it this one? Okay, this one, right? Okay. So because this is actually, you can hear this one is a beta, right? Okay, but you can see here, after we find the posterior, okay, right. The posterior is actually also beta. Oh, okay. So we can't really be, okay, right. So just take note, okay, right. Maybe, okay, over here, right? So if you can see over here, right? So this posterior is actually a beta, which is a beta y plus a, and then n plus b minus y. Okay, so this is actually a beta. So the posterior here is actually a beta. Okay, so this means that this example is if you have a beta, right? Then if you use transformation on this beta using phi theta y minus theta, you will actually get F distribution, right, which V1 and V2. Okay, so in this case, in the last example, right, what happens here is actually we have beta, let me see, what was it? Beta 22. Okay, so you can see over here, right, if you have beta 22, then y plus a equals to 2, n plus b minus y equals to 2. So that's why we actually have, yeah. Then if you can see over here, right, this is 2, 2. So actually you have your after transformation, we have a F distribution with V1 equals to 4, V2 equals to 4 actually. Okay, right. So I mean from this example, right, let me see, where is it? No, here. Okay, so meaning that if I have a theta, right, a posterior is beta 22, right? So, and then I use my phi is this one, theta 1 minus theta. Actually, my phi will have a F distribution, right, with V1 equals to 4, V2 equals to 4. Okay, so based on just our previous example, we have F distribution with 4 actually. Okay, and or if you look at the PDF, right, actually you can, this is your beta 22 and your phi, right? I mean, you can check this after you, if you put in your value, right? Okay, so actually we have your beta under this transformation, we have phi is F distribution for 4. Okay, because here actually your n, your a just now, right? If you remember, your y plus a is actually 2, and then your n plus b minus y is equal to 2. So this will be why this is your v1, v2 is 2 times 2, 4, 2 times 2, 4. So that's why you got f for 4. Okay, right. Then, okay, so now we have to compare the posterior summaries for theta and this theta and phi. Okay, so for the beta, right, the mean is alpha plus beta, so it's actually 2 plus 2, which is 0.5. Okay, and for the median, actually, right, for the median and mode, you have to find from the Google or whatever, because actually they don't or you can use the R. I mean, the median, you can use the R, right? But here, the median is actually 0.5, and the mode is actually 0.5 for beta to 2. Okay, and 95, and this one you can use R, right? If I use alpha over 2, meaning the quantile is actually, right? The quantile is actually 9, what call it, 2.5%, and then 97.2%. So I will get my 95% credible interval. Okay, so this is the value I get for my beta. Okay, right. Then, right, so this is where, you have to, you can see whether this is invariant or not. Okay, so for the F, this one also you have to get from R or from whatever. So anyway, the mean for F, F2 is actually 2. Okay, this one, you can check by formula or by R. Okay, and then you have 95% credible interval is 0.104. Then you have 9.6054. Okay, right. So when you have the distribution, right, you can find the mean, median, and mode. I mean, the mean you can calculate from the formula. Median you can get from R. I think mode, I'm not sure whether you can get mode from R. Probably you can. And credible interval also you can get from R. Okay, so the aim here is, you want to check whether it's invariant or not. Okay. Okay, I'll use. Okay, right. So if you look at the F, right? Okay, so the transformation is actually okay. The transformation is actually G phi is theta 1 minus theta. Okay, so this is your G actually. This is your G theta. Okay, so when you say invariant, what does it mean, right? Okay, I'll take the median, right? Okay, so if you see the median is 0.5 here, right? Okay, so if you look at the median of phi, right? So the value is the median of theta. The median of theta is 0.5. Okay, so if you put median of phi, we have to use this formula, meaning that you have 0.5 y minus 0.5. Okay, so meaning that you insert the median of theta inside your g theta function, right, using the same formula. So then you get this formula, and then you get 1. Okay, which is the same as the median from the distribution. Okay, so this is why I say median is invariant. Okay, but if you find the mean of phi, right, we use this formula. The mean of phi is actually, so mean of theta is actually 0.5. Okay, so so if mean of phi, if you use the mean of theta, which is 0.5, right, you actually get 1. Okay, and then it's not equal to 2, right? Because under the F distribution, the mean of phi is 2. Okay, so you can see that it's not the same as the mean from the distribution. That's why it's not invariant under the function. Okay, the same with the mode actually. If the mode is also 0.23, it's not the same as the mode which is 1. So again, it's not invariant. Okay, is it 4? Let me see. Okay, right. Okay, so but one thing about the credible interval, right? So if you look at the 95% credible interval, okay, right? So if you look at this is the original value of the credible interval 0.09. So if I were to use 0.094, was it? I put 0.943, okay. 943, 1 minus 0.0943. Okay, this will be actually equal to 0.1041. Okay, so this is actually, if you look over here, it's actually equal to the credible interval for your F distribution. Okay, and for the left side is actually 0.91. So for 0, I put 0.9057. Okay, 0.9057. 0.9057. So it's equal to 9.6045. Okay, so so if I were to use this formula and I put the credible interval, the lower limit and the upper limit, right, inside the formula, I will actually get the credible interval for the F distribution. Okay, so this is what I say, right? This is where it says like the median and the credible interval, which is the first quantile is actually invariant under the transformation, right? Because we just put the value inside this function g theta, and then we can actually get the median and the credible interval change from theta to phi directly, right? By using the formula. Okay, so that's one good advantage, right? But some for the mean, the mode, they are not the same. Okay, they are not the same value. I mean, they are not invariant. So you cannot get from the formula, you cannot just plug in, you cannot get the answer. Okay, right. Okay, so that's the end of the lecture. Right, do you have any question, class? Oh, record.